Hello, this is a video on one sample equivalence testing, which is a different form of hypothesis testing. So recall in a hypothesis test that our goal is to state a hypothesized value for some population parameter, like the population mean or standard deviation, and then perform a test, and the goal is typically to reject that null hypothesized value and accept an alternative. And in no way can we ever prove or demonstrate that a null hypothesis is true. We can simply reject it or not reject it. But there is actually another form of hypothesis testing that is not as well known, but often a better approach for inference in many scientific questions, and it's called equivalence testing. Essentially, in equivalence testing, we don't simply think about rejecting the null hypothesis. We think about whether any observed deviation from the null hypothesis is of any scientific or clinical importance. And if we determine that the observed differences are trivial, that is, of no real interest to us, then we will typically proceed and say, within some range or interval of values, as long as the theoretical mean is in that window, we're just going to assume the null is true. Hence the term equivalence. We simply say that whatever the theoretical mean or whatever the parameter is, we simply say it's equivalent to whatever the null hypothesized value happens to be. Okay. And the basic idea is to reverse the null and alternative hypotheses. So in equivalence testing, as you'll see in a moment, we're going to state two null hypotheses, and our goal is to reject both of them and accept an alternative, and those alternatives are what establish the range or interval of what we would call no significant difference or importance, we should say scientific importance, from a null hypothesis. Okay, and this idea of equivalence testing, basically we're saying within this window, as long as whatever the parameter value might actually be, as long as it's in that window, it's of no interest to it, it's not a big enough deviation or effect to concern us, we'll just assume the null value is true. And I would mention this is an interesting topic. It is weighing heavily into methodology the FDA is considering for the approval of what are called biosimilar drugs. And I won't get into a lot of detail, but basically traditional pharmaceuticals are often referred to as small molecule drugs, but there are new classes of drugs that are being generated or produced by genetically modified organisms, and these new drugs show a lot of promise in curing many types of diseases, but there are classes of these new drugs that are considered equivalent to some of the traditional small molecule drugs, drugs that you would be familiar with. The problem is the FDA is trying to figure out for existing drugs and how to compare these new biologic drugs to them, and what they're thinking about right now is a form of what we're discussing, equivalence testing. Is the new drug equivalent to the traditional drug? This is a hotly debated issue, and you'll hear more of it in the future because these biologics that are similar to existing drugs, there are probably 2,000 of them in the pipeline, and some of them may even be an improvement over existing drugs, such as antibiotics. Okay, so basically in equivalence testing, our goal is to show that within some window we can essentially assume the null hypothesis is true. And that window is determined by subject matter experts, and it's a window in which any deviation from the hypothesis would essentially be considered of no clinical or scientific importance. Hence, we just go ahead and assume the null hypothesis is true. And we're only going to concern ourselves with hypothesis testing and equivalence testing for the theoretical mean of a population. And the way the method works, and this is the most common method, as you're going to see in a moment, we're going to state two hypotheses, two nulls, and then we're going to use two one-sided t-tests to attempt to demonstrate equivalence. We're going to use a data set called CRI. CRI stands for Color Rendition Index. This is a measure of how well a fluorescent lamp renders color, and often fluorescent lamps do distort color, and there are ways that they measure it. In this particular case, the manufacturer of these lamps has specified a target value of 63 for CRI. CRI runs from 0 to 100, with 100 representing perfect rendering, and no light source ever actually reaches 100. So the target is 63, and engineers have decided that any difference plus or minus 6 units of 63 is of no practical significance. No one could ever detect the difference. Therefore, as long as the target for the process runs within this window, 63 plus or minus 6, they will just go ahead and assume it's running at 63. So again, the way the method works, we have to state two hypotheses. So notice the null hypotheses, one of them, the mean is less than 57, okay, but the alternative says greater than 57, so if we accept the alternative, we say that the mean is above 57. Similarly, the other null hypothesis says the mean is greater than 69. If we reject that, then we say that it's less than or equal to 69. So if we accept both alternatives, that is, we reject both of the nulls, then we can safely say that whatever the theoretical mean is, it's within this window. We're simply going to assume it's equivalent to 63. Okay. And currently, JUMP does not perform a one-sample equivalence test directly. However, there is an add-in you can use, or you simply go to the distribution platform and perform two one-sided t-tests. So we're going to illustrate this method using JUMP and the CRI example. So at this point, I'm going to bring over the CRI data, and the one sample t-test and the equivalence test are both done in the distribution platform. So I go to Analyze, Distribution. Okay, I have only one column, that is CRI, so that's the response. Okay. So in JUMP, by the way, notice we get a 95% confidence interval that says the theoretical mean is somewhere between 57.62 and 61.88. Notice that does not include 63, so that's an indication that maybe we are not going to be able to establish equivalence. Okay. However, we're going to go ahead and perform the tests. And by the way, in the distribution platform, you can form confidence intervals with other confidence levels. It's in the main report menu, okay, to the left of CRI, and just go down and select the value you want. But what we're going to use is test mean. Okay, so the first test, the hypothesized value is 57. Okay, so we're going to click OK, and JUMP performs a test, okay, as to whether the mean might be greater than 57. Okay, And I'm going to perform a second test. Okay, so I got a test mean. I type in 69. Okay. So notice what I'm interested in the first case, okay, is to show, okay, that under the alternative hypothesis that the true mean could possibly be greater than 57. Okay? And under the alternative, I'd like to show that it's possibly less than 69. So you're given the t-test values, okay, for both of the tests. So recall that under the null hypothesis, for the first test, okay, we reject the null that says we believe the mean is greater than 57, and under the second test, okay, we reject that the mean is greater than 69 and accept that it's less than 69. So notice the p-values are quite small. Again, you can see the results live. Therefore, even though we might reject the null hypothesis that the mean is 63, based on the engineering evaluation that a difference of plus or minus 6 is of no practical interest, we can go ahead and assume the mean is 63. This is where hypothesis testing differs from equivalence testing. So if we were to just do a test that the mean is different than 63, I'll go ahead and do that for you. I'll go to test mean, type in 63, okay, and we'll do the two-sided test. So we would reject the null hypothesis that the mean is 63. In other words, the difference between the observed value of 59.75 and 63 is significant. However, if we come back and we look at our equivalence tests, they tell us that whatever the observed deviation is, it is not significant. Because as long as the theoretical mean is within plus or minus 6 of 63, we can say it's equivalent.